Hello everyone, my name is Fernando Pereira, and today I will talk about Honey Potion. That's a compiler that translates Elixir to eBPF code. This is a joint work that I did with colleagues from UFMG, the university where I work, UFOP, and Cadence Design Systems. So the goal of this work is to do exactly what the title of the work says. We want to translate programs written in Elixir to eBPF. And here you might wonder why this work is sufficiently interesting to be presented at CGO, which is the conference where the paper was accepted. There are a few reasons why the work is worth to be presented at CGO. First, there is the fact that the gap between these two languages is pretty wide. Elixir is a high-level programming language. It's functional, dynamically typed, that we can use to write general-purpose applications. It was created by José Valim in 2012, about 13 years ago. Since then, it has acquired a pretty large community of users, being common in design and development of concurrent applications. In a sense, it resembles Erlang a bit. That's so much so that Elixir programs run on the Beam virtual machine, which is the Erlang VM. But the syntax is closer to Ruby, for instance. And then we have eBPF. It's an instruction set architecture meant to run within a sandbox Linux virtual machine. We can use eBPF to write network applications. We can inspect network packets, reroute them. We can inspect Linux processes, kill them, intercept system calls. Essentially, eBPF gives users the chance to write applications that will run with kernel privileges. So think about eBPF as a way to write signal handlers, exception handlers, I mean. Uh, there is a client program that runs with user privileges that might call these handlers. And the handlers run with kernel privileges. They do something that requires kernel privileges and then they return. But what's really very interesting to this work, at least from a compiler standpoint, is the fact that eBPF is a restricted programming language. By restricted, I mean to say that eBPF programs, at least when they run on the Linux kernel, they are verified. That's one of the few industrial quality programming environments that's verified by default. So to deploy an eBPF program in the Linux virtual machine, this program must pass the sieve of the Linux verifier. The verifier will ensure a number of things. There are two properties in particular that will be very important to us. First, every eBPF program terminates. Second, every memory access will happen within allocated bounds. Ensure termination is quite challenging in our context. We are compiling a functional programming language that's Turing complete to an environment that's not. So there will be programs that we cannot compile. In principle, we can compile a subset of programs that meet a property called primitive recursion. Recursive calls must be bounded and must terminate. The verifier, in turn, will ensure that the low-level program will not have backward branches. More yet, this program can only have up to 1 million instructions, so we are translating Elixir to programs without backward branches with up to 1 million instructions. The second property is that every memory access will have to be bounded, and the verifier must be able to determine that the access is bounded. That's particularly difficult if we remember that the eBPF stack contains only 512 bytes, and that a eBPF virtual machine can only use 11 registers. So we can only use 512 bytes of stack to translate a language where every call is inlined. The stack will have to fit the local variables and the spills, so we must be very frugal with space. But we can implement a heap. To do that, we use eBPF maps. These are data structures that the eBPF virtual machine uses to pass data between user processes and kernel processes. So, by the way of an example, here's an Elixir program. This is a simple program. It keeps a counter stored in a map, and increments the counter whenever function increment is called. And on the right, we have the equivalent eBPF program that we would get. I've simplified the program a bit though, just for the presentation. But we have instructions to initialize the counter. For instance, in this case, we use routines from the eBPF library, like map lookup element and map update element, to read and update the counter. We can load the counter directly in registers, as we are doing here, and then we increment this counter using a simple arithmetic addition. And then we can update the map using the built-in routine called map update element. So in a sense, what Honey Potion does is to translate an Elixir program, like we see here on the left, into an eBPF program, like the one we have on the right. But the path is much longer. There are a lot of hidden phases in this process, and I will explain them now. First, we do not produce eBPF code directly. Rather, we produce C code. So our target architecture is C, essentially. Once we have a C program, we use Clang to translate this C program to an eBPF binary. So here I'm showing a kind of program that we could produce out of our counterexample. I'm not really getting into the details, but notice that translating to C simplifies our job, because we can easily invoke eBPF built-in routines whenever we need them. And then we have two intermediate representations that we call Honey X and Honey C. They are both tree-like program representations. Honey X is very close to the Elixir AST, but it does have some properties. In particular, it's in SSA form. To produce Honey X, we use Elixir's metaprogramming capabilities. Elixir follows this tradition of Lisp-like programming languages, where code and data is pretty much the same thing. So the AST of a program is visible to the program itself. So we can traverse the AST of a program from within that program. In other words, we use Elixir's system of macros to expose the structure that encodes the program's AST. Therefore, we did not really have to write a parser. We already receive an AST that we can traverse. And then we traverse this data structure that exists in Elixir to produce the presentation that we call HoneyX. Notice that at this point, we no longer have recursive calls. They were all inlined. And at this point, we no longer have backward branches either. Every potential loop that could encode recursion has been fully inlined. And that's why it's easy to produce a program in static single assignment form. Essentially, we are translating a straight line program to SSA form. Then, after we did all this inlining, we translate HoneyX to HoneyC. This is again a tree-like program representation, but it's much closer to C than to Elixir. In particular, nodes have types. Some of these types can be generic because Elixir is dynamically typed, but many other nodes have types like int or pointer to int, for instance, and every node has size information. We need this size information, to implement the bound checks. That's necessary to pass the Linux verifier. It's at this stage that we also carry out several code optimizations that Honey Potion implements. There are three optimizations that we discuss in different sections of our paper, which are constant propagation, type propagation, and also partial evaluation. It's this combination of code transformation tools plus intermediate representations that we call the Honey Potion compiler. Something you may wonder is what we do with recursion. Elixir is a functional programming language and it uses recursion rather heavily. As an example, here's an example of a recursive program. That's a simple program, its semantics is not very important to the presentation. Just focus on the recursive call of sum. When sum is called from outside, then the caller must specify a maximum depth of the recursion stack with a special parameter called fuel. That's what we call the petrol semantics. Every function call has some fuel. Whenever recursion happens, fuel is decremented by 1. This extra parameter, fuel, is very important during code generation. It specifies by how much each recursive call must be inlined. After inline expansion, honeypotion does constant propagation. Constant propagation is very effective in our setting. For one, every fuel parameter must be a constant, and we can propagate this constant. Constant propagation usually will let honeypotion fold mutable code chunks into no-ops. As we are doing this example here, several assignments can be removed, for instance. Alongside constant propagation, we also do type propagation. The algorithm that works for constant propagation gives us most of what we need to implement type propagation. Type propagation is very useful because every eBPF program receives some parameter with well-known types. In this example, this parameter is the CDX variable. We know the signature of this structure and can use this knowledge to propagate types all over the Honey-C program representation. For instance, in this example, we are reading the PID field from CDX. We know that this field is an unsigned integer of 32 bits, and we can propagate this information down the tree representation. Type propagation let us replace operations and data representation with more efficient code. In this case, instead of having generic operations, we can use operations that work on integers directly, without having to load and check any meta information. But the most important advantage of type propagation is that it saves us lots of space on the stack. For instance, assume that we need to represent this tuple with 3 integers. A generic representation would take 68 bytes to store the tuple. First, we need 8 bytes to represent the bounds of the tuple, the beginning and the end of it. We need the bounds because every access must be bounded. That's to satisfy the verifier. These bounds mark the beginning and the end of the vector that stores the indices of the values within the tuple. And then we have the generic value. Each generic value takes 16 bytes to represent, and we have 3 of them in this example. We need 16 bytes in this case because we need to represent the type, which takes 2 words of 4 bytes, and then the value itself, which we also store always in 2 words of 4 bytes, thus 16 bytes. But with type propagation, we can store the whole tuple with only 32 bytes because we don't need to represent generic values. Instead of using 16 bytes, we can use only 4 bytes per integer value. Another advantage of the tree-like representation is that it really simplifies that code elimination. For instance, after we run type propagation, we can solve conditionals on either constants or on types. There are lots of conditionals that branch on types in honeypotion because, Elixir is a dynamically typed programming language. In this case, we can remove whole chunks of code, as we do in this example. Indeed, in honeypotion, this combination of straight-line code, full inlining, constant propagation, and that code elimination is pretty much equivalent to partial evaluation. And once we add in type propagation, we have full program specialization. The program is specialized for types and for constants. Optimizations bear an important impact on the quality of the code that we produce using honeypotion. For instance, let's take a look into the size of the programs that we produce without and with optimizations enabled. In this case, we shall be using some benchmarks that are available in the honeypotion distribution. 4 of these benchmarks are implementations of equivalent applications that were available in C, and then we just recode them in Elixir. And let's compare the size of the Honey-C representation of each program, considering the application of different optimizations. So size is measured in the number of nodes in the Honey-C program representation. Here's, you can see our results. It's a lot of numbers, so let's go over some of them. First, without any optimization in total, we will have 971 nodes in the Honey-C representation of these programs. With that code elimination, but without constant propagation, we lower this number to 927 nodes. Constant propagation, but no dead code elimination gives us 849 nodes. In this case, whenever an expression only involves constants, it's folded into a nobop. The combination of that code elimination and constant propagation gives us 670 nodes. That's to say that we could eliminate 45% of the code that we had with this combination of optimizations, which are indeed doing pretty much what we call partial evaluation of the programs. You might ask about type propagation, because I didn't really show it here. We cannot actually disable it. Without type propagation, we cannot compile any of these programs. They would require more than 512 bytes of stack. And you also might ask, is this code efficient? We can compare our programs with equivalent C programs. We have 5 equivalent benchmarks. The C programs were not implemented within our group. We implemented the equivalent honeypotion programs. And you can see that the performance is not very different. In at least one case, our program is even faster than the C program. But measuring the performance of eBPF programs is not very easy. They run really fast. We can more or less estimate the number of instructions that run per trigger of the eBPF handler by profiling the total number of eBPF applications on the eBPF virtual machine and then dividing the number by the number of triggers. But that's kind of just an approximation. But the fact is that if we can compile a program, it will run fast because it can have no more than 1 million instructions and no loops. So in the end, our performance is not too far from C. And the programs that we write in Elixir are twice as short as the programs that we write in C. Although the binaries are twice as large, honeypotion still inserts a lot of verification in the program. Remember, we are compiling a dynamically typed program language, so our binaries are not that small, but they have less than 1 million instructions. Otherwise we would not really be able to compile the code. And mind that the code is verified by default. If it compiles, then it passes the verifier. If it fails, then that's a bug in honeypotion. But in the end, what we have is a very nice compilation scenario where optimizations can be performed very aggressively, very extensively, even if the source language is not really Elixir. If you are optimizing a language that always terminates, well, enjoy it, because there are just too many things that we can do. So that was what I had to say. Our paper is available online at this QR code, and honeypotion is publicly available. Feel free to browse the code and perhaps send us a pull request at some point. And thank you very much for your time.